You see, and this is for prolet shape. This is the for prolet shape. Now, if in the question it is mentioned that the electroquadruple moment of the nucleus is negative, then in that case the shape will be oblate, and the shape of the oblate is like this. Okay, for simplicity, imagine that it is not oblate, it is omelette, like this, as I have mentioned in the picture. Hello, welcome to all to a new lecture on SSB lecturer physics solution 2023. This is the 17th number lecture of that series, and in this video we are starting from 81 number question. Okay, this is the 81 number question. The question is, the stable nucleus having radius equal to 1 by 3 of the radius of O5189 is, there are 4 options: helium, oxygen, nitrogen and lithium. That means we have to find the element among these 4 options whose radius is 3 times the radius of this element or nucleus. The nucleus is O5189, and no doubtly there is a printing mistake during typing this nucleus, that is O5189. In the universe there is no existence of this type of nucleus whose mass number is 5 and atomic number is 5 and mass number is 189. Okay, actually this is a element whose name is osmium. Okay, this is the element osmium whose atomic number is 76 and mass number is 189. Actually this should be printed here, but there is a printing mistake and we could not do anything. And I had raised an objection during the objection period of this 2023 paper, but they did not receive my objection. Okay, if they had received my objection, then they must have to give the grace mark, but they did not did that. Okay, why they did not approve my objection? Because in this question only we need the mass number. Okay, that is 189, and we don't need what kind of element it is or what is the atomic number of this nucleus is. Okay, so in proceeding to solve this question, you need nothing but a simple formula, that is R equal to R naught a to the power 1 by 3. Okay, where is the atomic mass number? 189. Okay, so if you see the solution, Rx by Ros, that is Rx means the radius of that unknown element that we want to find in this question, and Ros is the radius of osmium. Okay, radius of osmium we can calculate because the mass number is given 189. So you put here and make the ratio, and the ratio is given as 1 by 3. Then you calculate, simple calculation, derivation is here. Okay, so you will get 7, Ax equal to 7. That means the element whose mass number is 7. Whose mass number is 7? This is exist only for lithium. Okay, this is for lithium. This is for lithium. It is mentioned here, Li7. Okay, so coming to 82 number question, the question is given that the magnetic momentum of a neutron in terms of magnetic nuclear magneton mu1 is, okay, we have to find the magnetic moment of a neutron. How can you find? So before proceeding to solve this question, you should know that how many terms is contributed towards the magnetic moment for any kind of particle. One is angular momentum. That means for angular momentum, that means a particle, if it is moving in some angular or any path, circular path, elliptical path, then they will contribute a magnetic moment towards the net magnetic moment. Okay, and there is also a magnetic moment arises due to the spin angular momentum. Okay, but here for neutron there is no such angular momentum. So if there is no such angular momentum, there is no contribution of magnetic moment or angular magnetic moment towards the net magnetic moment. Why? Because there is no net charge on neutron. Neutron is neutral in nature. So if a neutral particle revolves around any particular axis, let's suppose z axis, then it will not contribute any magnetic moment because it has no charge as a whole. As a whole, when you consider a neutron, let's suppose this is a neutron moving in this path. This is the neutron. Okay, so it will not contribute any magnetic moment because it is neutral in nature. There is no charge because the angular momentum is denoted as this. This q is 0 here. So the magnetic moment for angular momentum is 0, but still there is angular momentum. Sorry, there is a magnetic moment due to the spin angular momentum. Okay. Okay, so but you should know how this spin angular momentum arises. For that you should know that there is an internal structure of a neutron, that is it consists of a quark, 2 down quark and 1 up quark. This is the structure of a neutron, where one is red, green and blue. Here this red, green, blue are the color quantum number to specify this 3 quarks. Okay, now you see, let's suppose this is our neutron which is spinning about this axis. Okay, this is the axis. About this axis this neutron is spinning. Okay, now if you see the neutron's charge distribution. Okay, neutron's charge distribution is this: a down quark, 2 down quark and a up quark. Up quark has charge how much? Up quark has charge 2e by 3, and a down quark has charge minus 1 by minus e by 3. Sorry, down quark has charge minus e by 3, whereas up quark has charge positive 2e by 3, where this e is the charge of a proton. Okay, positive charge. So these are the charges which are distributed inside the nucleus. Okay, now this charge distribution, if you draw a graph, okay, this is the charge distribution in this axis, and in the radius this is the charge distribution. If you see, this positive means there is a from this 0 radius to this much of radius there is a positive charge distribution, and from this radius to this radius there is a negative charge distribution, and there is a small positive charge distribution from this to this. Then the charge distribution vanishes. Okay, but if you now, as it is spinning, now if you imagine this is the neutron as a neutron, okay, and it is spinning, okay, then there is a net contribution of this charge, this negative charge area is larger compared to these two. There is a small positive contribution, there is a high positive contribution, but adding this positive areas contributions is smaller than this negative contribution. Okay, so there is a net negative magnetic moment for the neutron in case of a neutron. So that's why this the magnetic moment of neutron is minus 1.91. Okay, now if this is, I have done the derivation, I have not given any explanation, okay, or the derivation, because this is a, there are lots of derivation is involved here. Okay, you have to use the Schrodinger wave function, there are quantum mechanical derivations, there is a long derivation. Okay, I have skipped all those derivation and I have explained only in a logical way. Okay, and it is better to remember the final value, like for proton, like for neutron. For neutron, this is the momentum. Okay, magnetic momentum. Okay, actually this is the explanation, logical explanation, as the negative contribution is dominating the positive contribution inside the neutron. Okay, that's why this is the minus 1.91 is the correct one, where mu1 is the nuclear magneton whose value is 5.05 into 10 to the minus 27 joule into joule per Tesla. Okay, now coming to 83 number question, it is given that nuclear form factor is a Fourier transform of what? Option A, charge density, mass density, energy density, momentum of nucleons. Now let's see the solution. You see, the ratio of differential scattering cross section determined experimentally to the theoretical value is known as a nuclear form factor. Okay, this is the experimental scattering cross section and this is the theoretical scattering cross section. Okay, if you take the both ratio, you will get a nuclear form factor. Now you just see on this equation fq, q is the change in momentum of that experiment. Like if you apply electron on that nucleus, okay, for that electron, what is the change in momentum? That is q. Okay, so it is, if you see, this is integration of e to the power I q dot r rho r dqr. Okay, and here this rho r is a function of a charge. Okay, this is a function of a radius, but this rho r is a nuclear charge density. Okay, so that's why if you see, option A is the correct one. Okay, so option A, charge density of nucleus. Okay, now coming to 84 number question, it is given that if electric quadrupole moment of nucleus is positive, then the nuclear charge distribution is oblate spheroid, spherical symmetric, prolate spheroid, paraboloid. Okay, basically you have to find what is the shape of that nucleus whose electric quadrupole moment is positive. Okay, that's the main thing. Now see the solution. Remember that electric quadrupole moment is positive. Okay, now this is the electric quadrupole moment formula, and as there is integration is present, that means it is a what? It is a continuous charge distribution of a charge. Okay, now if you measure the electric quadrupole moment by assuming the measurement of a measurement axis as z axis, that means if you fix your axis as a z axis, and with respect to that you will measure all the quantities. Okay, so in that case the I becomes j. So when I becomes j, the quadrupole moment along z axis, okay, qzz will be proportional to 3z square minus r square. And as in the question it is mentioned that this is greater than positive, that means it is greater than 0. Okay, so when this term will be greater than 0, that means what? That means 3z square will be greater than r square, and you know the value of r square. R square is x square plus y square plus z square. Okay, so now on both sides, if you cancel one z square term, then you will get 2z square greater than x square plus y square. Okay, so z square plus z square greater than x square plus y square. Okay, so what is mean by that? That means the semi axis, the axis along x axis and the distance along the distance of axis along y axis, and their square addition will be less than the radius along z axis square, and that is 2 times. Okay, 2 times of a radius along z axis square will be greater than the x square plus y square. Okay, that means this is some kind of this type of shape. Okay, and if you could not imagine what is the shape of this type of a nucleus, then you imagine there is an egg and you are keeping that egg in this shape in your fingertips. Okay, like I have pasted the image in this figure. Okay, you see, and this is for prolet shape. This is the for prolet shape. Now if in the question it is mentioned that the electroquadruple moment of the nucleus is negative, then in that case the shape will be oblate, and the shape of the oblate is like this. Okay, for simplicity, imagine that it is not oblate, it is omelette, like this, as I have mentioned in the picture. Okay, you see. Now coming to 85 number question, that is the last number. Choose a wrong statement. It is asked you to find the wrong statement. So you see all the option one by one. In the option A, it is given that deuteron is loosely bound. This is the correct statement, because if you see the binding energy curve per nucleon, in that curve the deuteron is starting from the beginning. That means what? That means this is the least bound nucleus in the whole series, and whose bounding energy per nucleon is 1.1. This is the least bound, 1.1, and the highest bound is iron. This A56 26 20 Fe26 56, whose binding energy per nucleon is 8.8, the highest one. Okay, highly bound. Okay, so option A is the correct one. Now see option B. Option B is given that the parity is even for deuteron, and along the option B I am taking option D, because option D and option B are both are related. Okay, option D is given that the spin of deuteron in the ground state is 1. Now you see both, I am taking both at the same time. For this we have to find the state of a neutron and proton. Okay, now you know for a deuteron there is one proton and one neutron. Okay, so one proton is one and one neutron is present here in deuteron. Now if you place both neutron and proton, they will be placed in the ground state only, and the ground state is 1s 1 by 2. Okay, 1s 1 by 2, and in the 1s 1 by 2 the j value, that is the spin value, is 1 by 2, and the l value, that is the angular quantum number. Okay, angular quantum number, orbital angular quantum number, that is s. For s, l equal to 0. For p, l equal to 1. For d, l equal to 2, like this. Okay, so for proton this is the number, quantum number. For neutron this is the quantum number, and both are same as they are residing in the same state. Okay, now to find the spin of the nucleus you have to apply the Northern rule. This is the Northern rule. And why I am applying Northern rule? Because it is a odd order type nucleus. Okay, for odd order type nucleus you have to apply the Northern rule. And if you apply, and if this number, if this whole term you will give a even number, then the spin of that okay, so to apply the to find the spin of the nucleus you have to apply Northern rule. Okay, and this is the Northern rule. Why I am applying Northern rule? Because this is a order type nucleus. Okay, so for order type nucleus you have to apply Northern rule. And if this whole term give a even number, then the actual value of a spin of that nucleus is mod of a Jp minus Jn. And if the number is odd, then the actual value of spin is Jp plus Jn. For deuteron this number is odd, because you are getting 1 only. Okay, you are getting 1. So the spin of a deuteron is 1. So that's why option D is the correct one, because it has mentioned that the spin of the ground state of deuteron is 1. Now if you find parity is the combination of both proton and neutron, and the parity is minus 1 to the power Lp for proton, and for neutron minus 1 to the power Ln. And if you find the parity you will get a positive one. That means it is a even parity. For positive it is even, for negative it is odd. Okay, so both option A Option B and option D are correct one in terms of correctness, but we have to find the wrong statement. Now see option C. Option C is given that the probability of finding the neutron in a state D is more than state S state, which is a incorrect statement because the contribution or the probability of finding the neutron is more in A state as compared to D state. Okay. Now why I am telling? If you find, if you want to find, then you have to find the derivation. Okay, you have to do the derivation. Now we know that the ground state of the neutron is a mixture of both 3s1 and 3d1. You know that this is the ground state combination. Now if you apply the quantum mechanics to find the magnetic quantum number of this 3s1, then you will get this. Okay, this is the value magnetic quantum number for 3s1 state, magnetic moment. Okay, for 3d1 this is the magnetic moment. Okay, these value we are getting from calculation. Okay, theoretical calculation with the help of quantum mechanics. Okay, now this is the experimental value of magnetic moment of the deuteron. Okay, for deuteron this is the experimental value. Now if you want to find the theoretical value by using the quantum mechanics, then what you have to find? You have to find the wave function of that deuteron, and the wave function of any nucleus is a combination of a spin part, isospin part, and space part. Okay, so three combinations are there. Okay, so you have to first find the wave function, then you have to apply the formula like psi d mu d psi d. Okay, now if you calculate, you will get this. This is not equation 1, this is the equation 1. Okay, this cs and cd are the probability amplitude, and if you square them, then you will get the probability. Okay, so that's why ps pd are the probability. Okay, and we also know that cs square plus cd square is equal to 1. This is the basic statement. Okay, now if you solve this equation 1 and equation 2, then you will get the probability of a ps, that means the state probability of getting the neutron in the state S is 0.96. That means 96% probability that you will get the neutron, the neutron in the state S, CS1. Okay, and there is a very less probability of getting the neutron in the CS 3D1 state. That is 4%, only 4%. Okay, so hope you got the answer. Thanks for watching.